So let's start our lecture today. So I think last time last time I have the two sums, right? So I have the sums. So last time, so also we under the assumption that so the condition we are assuming is that we have A1 equal to K A2, and then for the K bigger than equal to 2, and also yeah, so and also there is a we have the lattices. And also like on the barrier L, so we have the sum as so first so this is a column sum, which is n squared times L minus 1 minus so yeah, so let me do this. So k squared times so these are the three terms. So let me just combine these two together. So L squared minus L. So it should be like L minus 1 times L times 2L minus 1. Yeah, so this is like L times L minus 1 for the sum of the squares, and then I have over 6. So this is like the column sum. Column n equal to L. And then plus and then I also have one copies of, so this is like the row m equal to 1. Okay, so and then I get so this is again L squared minus L, and then 2L minus 1 over 6 minus L minus 1 times mk squared, and then plus 2L cubed. So so this is like the row m equal to 1. Oh, sorry, this is m equal to, oh, actually, wait. Oh, okay. Okay. Yeah, so this is the column n equal to L, okay. So this is like L squared, okay. And then this is the row m equal to L, okay. So the m should be replaced by k. Sorry, the m should be replaced by L, right? Oh, okay. And then, so this is equal to what? So this is equal to L cubed minus L squared Okay. Shoot. It may still not right. Okay. So let me. Okay. So let me try this. So. Okay. So. So what are these equal to? So I get a k squared over 6, and then so this is equal to so 2l cubed, right? And then it is minus l squared plus 2l, sorry, minus l squared. Let me do it carefully. And then minus 2l squared plus l. And then here I get so this is equal to what? This is equal to 2l cubed minus l squared minus 2l squared plus l over 6. Yeah, so it should be this. And then minus so this guy is equal to l cubed k squared, and then minus minus becomes a plus l squared k squared plus 2l cubed. Okay. So let's see the coefficient for l cubed. So yeah, so it seems that so for l cubed, so I get, so this is 1 minus k squared over 6. Sorry, k squared over 3. And then plus, so this is L, so this is 1 over 3. And then I get minus k squared then so so for L squared, I get so this is -1 L squared term will be automatically it is not the dominant term. So dominant term is just L cubed. So so let's try this. So originally, so here, so I'm feeling this zero in again. So maybe I think maybe I should leave the 0 out. But instead of doing yeah, so let me see if I can leave the 0 out. And then what I can do is that I'm using the squares here. So so for example here this is up to m equal to k here, and then these are all zeros. So let's consider this square as a square, and then let's construct the square to be bigger and bigger. That potentially it could be less point, right? I don't know whether this would converge or not. Yeah, so this one I don't see this argument. Yeah, so let's try let's try this one. Yeah, because yeah, so then so so namely the reason why I failed here is that the coefficient of this L is for the Q power is not equal to 0, and it's not equal to 0, and for the denominator, so the denominator basically so I'm using the lower bound as the lower bound is like k squared. So I want to use the lower bound as so intended lower bound. I'm using the intended lower bound as k squared L squared plus 1 over k squared squared. So in this scenario, so I will have L to the 4th power as the denominator here, and since this it won't give me the results that so yeah, let's think of the reason why this why we can cancel them out. Let's think of this reason why we can cancel them out here. So yeah, I think um, yeah, let's try this. Let's try this. Shoot. Okay. So on the square, let's see. So the first k by k square. So so what sum would I use? So namely, I want to find a so let's consider the summand. Summand will be so namely I would sum from so n from 1 to k minus 1 of yeah, so I'm summing over all the points for the first k by k square. So namely, I'm just ignoring this line, this vertical line, and then I'm summing over so things to the left of the line, of the vertical line. So here I'm having n from 1 to k minus 1 of n squared, and then I'm summing this n from 1 to k. N squared minus mk squared. So this gives me, so yeah, I'll choose a lower bound later, so the denominator. So so first, so Oh, okay. So let's briefly indicate it. So when m equal to 1, so we get a sum as I think it's k minus 1 times k times uh, 2k minus 1, right? Over 6. So this is n here. And then, so minus k squared. Yeah. So for each m, it will be the sum of the square of n minus, like the m squared k squared, right? So here, when I sum over, so for any m, right? So for any, so fix any m, so it will be just the m k squared, right? So sorry, m squared k squared. And then when I sum over m, so of this guy, it will give me, so it will give me k squared times k minus 1 times 2k minus 1 over 6. So and then, so this guy minus k squared times, so this is equal to, sorry, let me recall the formula again. So this is equal to k squared times k times k plus 1 times 2k plus 1 over 6. So eventually what I get is that so this is equal to, so first I have, let me do it carefully here. So k squared times, so this is like 2k squared, right? Minus k minus 2k plus 1. So over 6 minus, so here what I get is that it's give me why it's like fifth. Okay, so n part is almost negligible. So okay, sorry. So k squared this is times this is k cubed. Okay, so k cubed times 2k squared plus k, so 3k plus 1 over 6. Okay. So for the denominator, so what do I get for the denominator? So what is lower bound? The lower bound is 1, 1, right? So it's yeah, I think it's so you have so let me so we plug in 1, 1. So namely you get if you plug in 1, 1, you will get n to the you will get n to the you will get k to the fourth power. So the lower bound at 1, 1, which is equal to the lower bound for the denominator. 1 is equal to 4a2 times 1 plus k squared. So let me do a second one. So n equal to 2k, and so these are like the missing points here, and so this is another square. Let me see. So here let's continue, and then so this is all the way missing up to here, n equal to 2k. So I'm doing this one. So this one, I think I can have some breakdown, right? So I can break it into 3 pieces. So let's label at 1, 2, 3. So if I'm on region 1, what I have is that I'm using my sum to be so n from n from k plus 1 to 2k minus 1, and then I'm summing over m from 1 to k, right? And then n squared minus m squared. So so it should give me m from 1 to k. So here, what I have is that so let me use the formula. So here, what I have is so let's first sum over the 2k minus 1 times 2k times 4 should be 4k, right? I think. Yeah, should be 4k. Wait, no. 4k minus 1. Yeah, so it should be 2 times the total sum. So yeah, so so two times the sum, the number of terms that's being summed, which is 4k minus 2, and then plus 1. So it should be 4k minus 1, yes. And then minus. So when I sum from n to, so how many copies are there being summed? Should be so this one minus so k minus 2. No, can't be possible. Oh, okay. So yeah, k minus 1. Sorry, k minus 1. Yes, times nk squared. Yes. And then this gives me, so this is the copies of k. So so k times 2k minus 1 times 2k times 4k minus 1 minus. So now I'm having k squared. Oh, sorry. I think I need to subtract the lower case. Yeah. So here I should subtract subtract the sum from the first k sum, right? So I should subtract the first n from 1 to k. So basically, so k times k plus 1 times 2k plus 1. Oh, sorry, this whole thing is over 6. And then minus. So here I get, so this is k minus 1 times m squared k squared. So yeah, so this gives me k times I think it's more efficient to just focusing on the highest power here. So so here this one is 2k, 2k. So yeah, so this is k times 2k minus 1 times 2k times 4k minus 1 over 6. And then yeah, so this is like k squared k plus 1 2k plus 1 over 6. And then, so we sum over k. So this gives you k times k plus 1 times 2k plus 1 over 6 times k minus 1 k squared. So when I focus on the highest power of k, so this gives me what coefficient? 4 times 4, which is 16, and then 16 over 6. K, 1, 2, 3, 4. K to the first power plus some remainder, and then plus minus. So here I have 1, 2, 3, 4. Yeah. So highest power is 2. So 2 over 6. K to the first power minus some remainder, and then minus. So here I get 1, 2, 3, 4, 5. Yeah. So this is k to the 6th power. So the coefficient is 2, right? And then plus some remainder. So yeah, I think this estimate, I think is not it's not fitting fitting in this scenario, because so if we pick like so basically I think it is somehow a little bit not sharp enough, because if we fix a point, let's say using this point, then wait. this gives me 7 over 3 k to the 4th power minus 2 to the 6th power. So remaining. So so let's look at the second one. On 2, so what we have is that we have the sum as so in this case the n goes at also the same and then the m goes at so now it starts at k plus 1 and then it ends at 2k so also n squared minus m k squared, so it will give me same sum for n of so for the n part, it will be invariant because for each of the m you are sum here, right? So because the inside basically is the same for each m, and when we are summing over m, this n remains unchanged. So you are basically just summing over k copies of the things inside for each of the m. So what I get is that I'm getting so I need I just need to consider the case where the m is the sum for m here. So I should get also 7 over 3k to the 4th power. So this is from the part from n part, and then plus. So now I'm summing over the mth power here. Okay, so I should be using this one also. So it should be minus sum, which is k minus 1 times m squared k squared. So this is equal to here so let me pull out a k minus 1 times k squared. And for the m sum, so for the m sum, I need to sum over all the so 2k 2k plus 1 4k plus 1 over 6 minus sum over k times k plus 1 times 2k plus 1 over 6. So I should get, so let me just count the highest power here. So this is like 4 so plus minus, so here I'm having 8 over 6, and then here I'm having just 2. Okay, to the 6th power. So I get exactly 1. No. So this is just, this is sorry, this is 16. And then so let's also consider the case of 3 here. Oops. So on 3, so we have this n sum as n from also 1 to k minus 1, and m from k plus 1 to 2k minus 1. Oh, sorry, 2k. And then what I have is so I have sum as so for the sum, so I think I will have the same sum as the sum here for the end, right? So here what I have is I'm having So it's like the power for n is like uh, 1/3 k to the 4th power plus some remainder, and for the sum of the mth power. So I think it will give you something like this, right? Yes, it is exactly k minus 1 copies of for each m, right? So there is exactly k minus 1 copies of mk squared, and then you are summing again using again using m plus k plus 1 to k. So therefore you will get you will get the same band. So so it will be minus 16/6/14 k to the 6th power plus some remainder. Okay. It seems like for each of the columns here, I will be having the same m, right? I will having the same m being subtracted from here. Right? Wait, no. Wait, what do I get in common? So so for each level, yes. So for each level, so for each horizontal level, so I'm looking at, so this is the first one, right? So the coefficient for m is, wait, I think there's some problem with this one because it should have, I think it has k to the 6th power somewhere, right? But why it is having yeah, I'm expecting something to be so k to the 6th power. So where am I doing wrong here? Oh, yes. So here it should be, I'm forgetting to multiply a copy of k here. So because I'm summing over this guy, right? So here, what I do before I just substitute, I will call k squared here, and then this is the sum of the m's from 1 to k. So I forgot to add the k here. So eventually, let's put a square here, and then this is to the 4th power. So it is like 1/3. It is like minus 1/3 k to the 6th power. Yeah, so this is like this one. Yes, so this is in 1, right? So for each row, I'm having the same k. I'm having the same m values for the, yes. the same m part. Yeah, the same m part. I'm having the same m part. So can I do something with that? Can I do something with this one? But okay, so the problem is that the denominator is causing us some trouble, right? Yeah, let me see. I want to see whether this m is so are they always gonna increasing or decreasing? Let me see. So it seems like this m power is getting more and more negative, right? Because when you are, so here you are like subtracting this term, right? And then you pull out like the k minus 1. Wait, I think I make a mistake. So right, I think I made a mistake here. So it should not be exactly k, right? So even though it turns out to be like the same, but I should exactly multiply by k minus 1. Sorry, yeah. So because this is adding up k minus 1 copies of the n, so therefore you should get like k minus 1, and also yeah, but maybe I write this one. So k cubed times k minus 1. Okay, here we go. And then for this one, so why the sum is getting more and more negative? Because basically you are so this term is getting larger and larger when the actually wait on 1 second. So yes, so basically this is like the yeah, so this accounts for levels for m, right? So this accounts for levels for m. Yeah, so that's yeah. So here yeah, I would say that sort of explains why, so at the same level you are having the same sum. So as the levels is getting bigger and bigger, you may expect this guy to be bigger and bigger, and this one to be also bigger, but not so big compared to this guy. So I'm expecting the coefficient to be bigger and bigger. Okay. So so how does this imply in our scenario? So okay. So so let me pause here. So I will continue next time. Thanks for watching.